In this video, we're going to learn about the domain and range of standard functions. So before we can actually talk about functions, we need to actually define what domain and range are. So domain is actually going to be all the possible values within our function that are related to usually what we consider as the x variable, from left to right, from negative infinity to positive infinity. And whatever values that, say if we have a function that looks like this, which in other words are just all the values that we can plug into our function, or plug into x. Now let's say for instance that we have a function that looks something like this. Our domain is going to be all the values that we see from negative infinity to positive infinity. And we're going to say that this function right here, it has something called an asymptote. And an asymptote means that a value approaches, but it never actually crosses that. And this asymptote is going to be set at x is equal to 0, meaning that our function will either never go to 0 or it will never go to infinity. It cannot be any of these values here. So when we write what the domain is, we usually put it with a d and colon. And what we're going to say is we'll put this in parentheses, which we call for domain is usually open brackets. We say that this is going to go from 0 all the way to infinity. And so we write it like this, where it's open brackets. If by chance we have a function that starts right here at 0 and continues on, and we'll say that it continues on into infinity in terms of the x-axis, we could actually write that domain with a closed bracket, which looks like this, meaning that it does include 0 and it goes to infinity. Now infinity is not a defined number, and that's why we actually keep it as open brackets. Now moving on to our range is actually going to be all possible values of y, or typically y. It's what we see as our dependent variables, or what the function produces. So we look at that from negative infinity for the y to positive infinity as the y. If, for instance, we have a function that looks like this, and we have an asymptote set at y is equal to 0, we know that for all values in our range, which we denote as a capital R with a colon, we would say that our range would be from 0 to positive infinity, which we would denote like this. Now we have to make the distinction that we are looking at values of y, so we have to make sure that we're looking at the vertical axes and what those values would represent. So we know that for this function we're actually looking at the positive values of y, which go here to infinity, even though we're looking at our x-axis and this is negative values. We want to consider only what is going to be for y. Now let's say we have an example of a function that starts right here at negative 2, and it actually does begin at negative 2 and it goes into infinity. Again, when we would write this range, we're going to put it as a closed bracket because it does include the value of negative 2. Again, remember this is going to be y, so 1, negative 2, and then we're going to go to infinity since this continues on. Moving on now, we'll take a look at line. Now we can write this in a simple form as y is equal to x. And if we were to graph it, it would look something like this. It would go to positive infinity and negative infinity for both x and y. And we could also think of it this way. Anytime that we input a value for x, which we are going to consider as our domain, what we input in, we will get the same output that we see here. So we can choose any value that we want. That would mean that we're going to have a domain of negative infinity to positive infinity. We can also see this as in the graph that as we continue, it's going to continue positively and it'll continue negatively from the left. Our range will be the same thing. Our domain will actually be from negative infinity to positive infinity, meaning our values for y will increase negatively to infinity and all the way positively to infinity. And this is going to be the same for y is equal to mx plus b, our standard equation for a line. No matter whatever values we change for b or for m, we will always get a domain and range from negative infinity to positive infinity. Moving on to absolute values, so that's going to be looking like y is equal to the absolute value of x, meaning that any value that we put in, whether positive or negative, will give us a positive value. The function looks similar to this, where we actually have a slope of 1 on either side. So when we look at the domain of this, we're going to be looking at the x values, and we can see that it's going to be from negative infinity to positive infinity. However, for our range, we're actually going to see that it starts at 0, but it can never get below 0. So we're going to have a closed bracket here for 0, to infinity for the range. If we take a look at it in terms of the standard form of the equation, where we get y is equal to a, which is going to be a multiplier, times the absolute value of x minus h, which will set our x-intercept, plus our value for k, which will be our y-intercept, we can actually determine what the domain and range of these values are. The values of h and k will determine our vertex for that, meaning this point right here. So if we had a point right here, which we call as -3, 2, that's going to be our vertex for where we set this off. And a will actually change the slope of the line. Where we get a bigger value will be a more increased slope up, and versus the other way, which will get a more sideways slope. H does not determine any sort of change in the domain. Our domain for the standard equation will always stay the same. However, the value of k is actually going to determine our value for our range. And that's going to be equal to k for the start and to infinity for our range. The value of a will actually determine our range. And if we have a positive value for a, we'll have our range look like this. However, if a is going to be a negative value, this actually flips our range to being where we'll see negative infinity to k. Now the quadratic formula is going to be equal to y is equal to x squared for a simple formula, and that's going to look something like this. It'll be similar into the idea of what our domain and range are for the absolute value, where we're going to have negative infinity to positive infinity for the domain, because it can be all values for which we input into x. However, our range is going to be again from 0 to infinity, meaning that we can never have a negative value for something that's squared. If we take a look at the standard form of the equation, that's going to be a is equal to x minus h squared plus k. Again, the value for x and h will determine where our vertex is, which we see here, and it'll depend where actually we'll have our values for the range, similar to the absolute value. Given the standard form, actually we would find our vertex by solving for h is equal to negative b over 2a, where if we factor out this equation, we'd be looking at ax squared plus bx plus c to solve for the quadratic, which we can find the vertex again from here. Now again, for the standard equation for our domain, it will always be negative infinity to positive infinity. Our range will be determined actually by what we see for our vertex or for what value we see of k. And we can set this as k to positive infinity. Now we could also see this as c or k for the same value which we'll put here. However, this is going to be for when a is greater than 0, whenever we have a positive a that's going to be multiplied to x squared. If a is a negative value, again, we're going to flip the range to be where we actually see from negative infinity to k or to c, which will be closed brackets. For a cubic function, the simple form is going to be y is equal to x cubed. Now the standard form is actually going to be similar, as we'll have y is equal to a times x minus h cubed plus k. However, no matter what we have for the equation, whether it is standard or simple, we will have a value for domain that will always be from negative infinity to positive infinity. And for a range, it will always be from negative infinity to positive infinity. No exceptions. Now, a square root function is going to be y is equal to the square root of x in a simple form. That takes a shape that looks similar to this, where we actually can plug in 0 and get a value 0 out. So that will set our domain to be equal to close parentheses from 0 to infinity, and our range the same, from 0 to infinity. If we look at the standard form of this equation, we're going to have y is equal to a times the square root of x minus h plus k. This will determine that our domain is actually going to be from h to infinity, and our range from k to infinity. Again, if a is going to be a positive value, we'll see this result for these two. For a is less than 0, or we have a negative number, again, we're actually going to be keeping the same domain because we always have to have a positive value with inside of that square root sign. However, our range will be flipped, where we're actually going to go from negative infinity to k. Now, a cube root function, we can see a simple form in terms of like this, where we have x raised to the cube root. And this is going to look something like this. The standard form of this equation is equal to y is equal to a times the cubed root of x minus h, with h inside of the cube root, plus k. For all values of domain and range, no matter if we change an h or a k value, is going to be negative infinity to positive infinity for both the range and the domain. Our reciprocal function, the simple form, is going to be 1 over x. And this will take a shape such as this right here, where we actually have an asymptote at both x is equal to 0 and y is equal to 0. And this will determine actually our values for the domain and range. So our domain is going to be from negative infinity to 0, both open brackets because it can't accept 0, and 0 to infinity. And that'll be the same for the range, where we're going to go from negative infinity to 0, and then 0 to infinity. If we look at the standard form of this equation, we're going to have y is equal to a over x minus h plus k. And this will actually determine what our values for the domain and range are going to be, where we're going to have negative infinity to h for our domain, and from h to positive infinity. For our range, it will be similar, but with k. So we'll have negative infinity to k, and then k to infinity. Our values of a won't determine any sort of change for domain and range. That is because we actually see the full length of both x and y. It's just where the asymptotes are set will actually determine what values we can't have. The reciprocal squared is going to be the function y is equal to 1 over x squared. And it'll look similar in shape to this, where we see that we have all values positive y. And we have two asymptotes, one at x is equal to 0 and one at y is equal to 0. This will set our domain to be equal to negative infinity to 0, and then from 0 to positive infinity for the x values. And for y, we're actually going to see from 0 to positive infinity. We can't have any negative values for y. If we take a look at the standard form of this equation, we have y is equal to a over x minus h squared plus k. This will change our domain to be at negative infinity to h, and then h to positive infinity. Our range is going to be equal to r is equal to k to infinity. And again, our values of a will determine what changes for our range. So any positive values for a will be this example here. If a is a negative value, we're actually just seeing that our range is going to flip, so our range will be equal to negative infinity to k. When we look at exponent, we're going to be looking at a function where we have y, say, raised to the b to the x power. Now, b could be any value. It could be 2 to the x, it could be 3 to the x, it could also be e to the x. And if you remember, e is equal to roughly 2.718 raised to the x. Now, a function of an exponent will look something like this if we have exponential growth. Now, exponential growth is where we have a value of b is greater than or equal to 1. If, say, we have a value of b where it is less than 1, but also greater than 0, we would have a graph that would look something like this. And that's going to be exponential decay. For both of these graphs, we're going to still have an asymptote at y is equal to 0. That domain that we're going to see for this function is going to be from negative infinity to positive infinity. And our range is going to be denoted by that asymptote, so we're going to see from 0 to positive infinity. Now, the standard equation of this graph is going to be y is equal to a times b raised to the x minus h. Outside of parentheses, we'll have plus k. This will not change our domain, so our domain is still going to be from negative infinity to positive infinity. However, this will change our range, where we're going to actually go from k to infinity. And again, it will be open brackets. It cannot actually equal that value of k. Now, this is going to be for the case where a is greater than 0, so we have a positive value here for a. If we have a negative value for this, we're actually going to see that the range will be flipped. Our domain will stay the same, and so we will continue seeing domain of negative infinity to positive infinity. Our range, however, is going to be flipped to negative infinity to k. Whenever we're looking at logarithms, we can see this as log of some sort of base, usually it's denoted as b, to x. We could also see this as natural log of x. This graph will look something like this, where we have an asymptote at x is equal to 0. So our domain for this function is going to be from 0. It does not actually include 0. And our range is going to be from negative infinity to positive infinity. The standard form of this equation we usually see as a is equal to a times log base b of x minus h in parentheses plus k. This will change our domain to where we go from h to infinity, and our range will stay the same from negative infinity to positive infinity. Now again, this is going to be for when a is a positive value or greater than 0. For when a is less than 0, our domain is going to change to where actually we go from negative infinity to h, and our range, though, will stay the same, be from negative infinity to positive infinity.